In today's lesson, we're going to learn how to simplify square roots. First, two properties. The first is the product property. That tells us that the square root of AB, the square root of A times B, is equal to the square root of A times the square root of B. For example, if I had the square root of 2 times 4, I could split that up into two separate square roots, the square root of 2 times the square root of 4. And just note that this is the product property because we're multiplying. This only works for multiplication. You cannot do this if there is a plus or a minus in between the A and the B. But we do have a quotient property for division. If you have the square root of a fraction, the square root of A divided by B, I can split that up into two square roots, the square root of A divided by the square root of B. The square root of the numerator divided by the square root of the denominator. And we're going to use these properties in order to simplify some square roots. Remember that you cannot take the square root of a negative number, because when I take the square root of a number, I'm looking to see what number or expression times itself gives you the number under the radical. And it can't be a negative value because there's no number times itself. That would be a negative. Let's try out these examples on some paper. So first I'm going to take the square root of 81. So when I ask myself, what number times itself would give me 81? 9, because 9 times 9 is 81. So the square root of 81 is 9. The next question, square root of 0. Well, what number times itself would be 0? 0, right? Because 0 times 0 is 0. So it's still a 0. Square root of negative 25. So that's asking me what number times itself would be negative 25. Hope you remembered that we just said you can't take the square root of a negative number. So this doesn't have a real solution. So you can either write no real solution, or you can write undefined. And we will accept either. But it's not going to be 5 because 5 times 5 is positive 25. And it can't be a negative 5 either because a negative 5 times a negative 5 is still a positive 25. So no real solution. Square root of 12. So what number times itself would be 12? Well, I'm not really going to be able to do that. There isn't a number times itself, at least one that's not a decimal, that's going to be 12. So how can I simplify this value? What I'm going to do is something called prime factorization. And that means I'm going to take the number 12 and break it up into prime numbers. We do that by first thinking of any two numbers that multiply to 12. The first one I think about is 3 times 4. Then you want to take any that are not prime and keep breaking them down. So 3 is a prime number. 3 only can be broken down into 1 times 3, so I can stop with 3. 4 is not prime because I can keep going and make it 2 times 2. But 2 and 2 are both prime, so I'm done. So the prime factorization of 12 is 2 times 2 times 3. So I'm going to rewrite this as the square root of 2 times 2 times 3. And this is where we're going to use some of our rules that we just learned. So first, the product property says that if I have some things being multiplied inside of a square root, I can break them up into multiple different square roots. And that's what I want to do. But I don't just want to break it up in any way. I want to break it up so that I can take the square root of at least part of it because I can't take the square root of all of 12. So how do I get something that I can take the square root of? Well, I know I can take the square root of a number if something times itself is that value. And I see here that I have two 2's. So 2 times 2. I can take the square root of that then, because 2 times 2 is 4. The square root of 4 would be 2. So we're going to break that up into the 2 times the 2, and then the 3 is in another square root. So the square root of 2 times 2 is just 2. Again, you can think of this as 2 times 2 is 4, and then the square root of 4 is 2. Or this is really 2 squared, and the square root will cancel out our squared, leaving us with just a 2. So my answer is 2 times the square root of 3. Let's try another one. So this one is a fraction. So I'm going to use my quotient rule first and rewrite it as the square root of the numerator divided by the square root of the denominator. So I have a 32 and a 49 and also a variable. We'll come back to the variable, but let's talk about the numbers first. So 49, that one you should recognize as a perfect square. The square root of 49 is just 7. So that part was easy. 32 is not a perfect square. So I need to break down 32 into its prime factorization to find any perfect squares in there. So 32, what can I think of that multiplies to 32? How about 8 times 4? 8 can be 4 times 2. 4 is 2 times 2. All the 2's are prime. And then 4 is yet another 2 times 2. So I'm going to rewrite this as 1, 2, 3, 4, 5 2's all being multiplied together. And so for every group of 2, every pair of 2 that I can make, the square root of a 2 times a 2, or the square root of 4, is going to be 2. If I can make a group of 2 that's 2 squared, I can take the square root of it. You're left with a 2. I can make another group of 2 that I can pull out here. I do still have 1 left on the inside. I'm going to leave a space here because I still have to talk about the x's. Put that leftover 2 still inside the square root, and I still have that denominator of 7. So what do I do with these variables? Well, pretty much the same thing I do with the numbers. With that 32, I broke it down into its primes. With my x's, I can break it down into individual x's. So I know x cubed is the same as x times x times x. And to get out of the square root, I need a group of 2. I need something times itself. So I can make one group of 2 x's. So the square root of an x squared is an x. There's one x left over, and that's going to stay on the inside. The last thing I can do is simplify this part. I have a 2 times 2 here, and that is a 4. But everything else will stay the same. Let's try the next one. 44xy squared z to the 5th. So 44, that's not a perfect square, so I'm going to want to break it down into its primes. 44, I think about 4 times 11. 11's prime, and that's 2 times 2. So I'll take that and rewrite it as a 2 times a 2 times an 11. There's one x, y times y, z times z times z times z, one more. So we want to make groups of 2. I can make a group of 2 2's. There's only one 11. There's only one x. I've got a group of 2 y's, one group of z, another group of z. There's one left over. So we can take out 1, 2, 1 y, 1 z, and another z. So I could write z times z, but I would need to simplify that. So I might as well just write z squared. And left inside is the 11, 1x, and 1z. And I also just want to show you over here, if you break down that 44 into 4 times 11, the square root of 4 is 2, and then I leave the 11 on the inside. So you can, if you notice the perfect square, you can just leave it as a 4 and say, what's the square root of 4? It is 2. On to our next slide. After you simplify any radical, you want to multiply any numbers or variables that may be in front of the radical. So if you end up with multiple things in the front, you can multiply them together. Let's see some examples of that. Let's try this one. 2 times the square root of 64. Well, let's deal with the square root of 64. That's a perfect square, so that's nice. So it's 2, and then the square root of 64 is 8. When there's no symbol between two things, you're multiplying them. So this is 2 times 8, which is 16. X times the square root of 32. So to simplify the square root of 32, we want to break it down and see what perfect squares we have in there. So I can make this 8 times 4, 4 times 2, 2 times 2, and there's another 2 times 2 in there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Want to make groups of 2. Square root of 2 times 2, we can pull out 1, 2. This x is already there, so I'll pull out a 2, pull out another 2. This 2 is still left. And then I'm just going to multiply all this stuff together. 2 times 2 is 4 with the x, square root of 2. Remember that we always keep our leading coefficient, the number in the front, and then any variables. Now I have the square root of a fraction. That's my quotient rule. I'm going to keep this 2x and rewrite this as the square root of 1 over the square root of 4. Well, 1 and 4 are both perfect squares. The square root of 1 is 1, and the square root of 4 is 2. So what is 2x times 1/2? Well, the 2's will cancel. Times 2 divided by 2. 1 times x is just x. How about this one? Square root of 13 squared. Well, I know 13 is not a perfect square, so my next step would be, okay, let me try a prime factorization, see if I can find a pair of numbers. But 13 is prime, so I can't break it down, which means I can't simplify the square root of 13. But if I'm taking the square root of something and then squaring it, what's going to happen? Well, squaring and square roots are inverse operations. So think about what would happen to a number if I added 5 and then subtracted 5, or if I multiplied something by 5 and then divided it by 5. You would end up back where you started, right? Because those are inverse operations. So squaring and square roots are inverse operations, so they're going to cancel each other out. So if I square the square root of 13 squared, I'm just going to get 13. All right, now I have 2 square roots being multiplied. Well, I cannot simplify either of these because 3 and 5 are both prime, so they won't have any pairs in them. But I can combine them together, pretty much just going to use the opposite of that product property. Instead of splitting up something into 2 different square roots, I can combine them back together into 1 square root, the square root of 3 times 5, which is the square root of 15. And I know I can't simplify this any further because 15 just breaks down to 5 and 3, and they're 2 different numbers, so I have no pairs. And my last one, square root of 8 times 3. There's 2 ways you could do this question. One is to combine them together at the beginning. I can say 8 times 3 is going to be the square root of 24. And then you'll want to break down 24, which I think about 4 and 6 first. And then I can break this down to 2 times 3, and this is 2 times 2. So that means I have 2 times 2 times 2 times 3. I can make one group of 2. So I pull out that 2, and you're left with that 2 times 3, which is 6 on the inside. The other option is instead of combining them right away, you can simplify them first and then combine them. So if I start with simplifying 8 and 3, I can't simplify 3, but I can simplify 8 because 8 breaks down to 4 times 2, and there's my perfect square, which is another 2 times 2. So that's going to be 2 times 2 times 2, and then still square root of 3. There's my pair, 2 square root of 2 times the square root of 3. And then I can combine the square roots together. I still have a 2 on the outside, and you combine the 2 times 3 to get 6. So you get the same answer either way.